So in this video, we'll be going over the process of setting up analog servo drivers, and here we have an older 1280 M5 profile. So the visuals that you're going to be seeing on your main screen and in this video will likely be different if you're using our newer 1366 profiles, but the setup process is still the same, it's still the same logic, despite looking a little different. And here I have an ET10 myCNC controller connected, and I also have connected one servo driver, and it's a Yaskawa from around 1991. So you know that it's not the most recent, it's not the best, it hasn't been fine-tuned or anything, so we are going to have some error, that's going to be visible once we set this up. So here we're going to be going into our settings, into our configuration dialogs, and then into the encoder tab. And within this tab, first of all, we'll be setting up the encoder resolution to correspond to the actual encoder resolution that we physically have in front of us for the motor. And we know that the encoder resolution for the motor is 2048 or 2048. So out of the list that is presented to you, if you click the button, we will choose 2048 and then press the save button. So in this case, we haven't actually sent the servo on signal, so we can just move the rotor manually. The servo is currently off, so you can just see the encoder values as they are changing very rapidly. Nothing is impeding them. There's no resistance, nothing like that. So next, we want to set our mul and our div values. So that's our multiplier and our divider. And with analog servo drives, we want to have the resulting value, so the value that results from having the multiplier divided by the divider, we want that value to be equal to 1. And if you're using, for example, not the analog servo drive setup, but rather a pulse dir and linear encoders for your error, then the coefficient that you are looking for will most likely not be equal to 1. It will not be the same as in the case of this example, since the resolution for both the motor and the linear encoder will likely be different. And then you will have to account for that and have a coefficient that adjusts and converts one to the other. But in our case, it's just a simple coefficient of 1. And just based on how the software operates, we cannot have our div value, the divider, equal to 0, and the minimum value that we can have is 1. So here we can set the values to be 2 for the multiplier, and then that 2 will be divided by 2 to the power of 1. As a result, that whole value will be equal to 1. And that might seem a little complex, but really all you're doing is you are having this equation. You have the multiplier divided by 2 to the power of the divider, and you are just looking to have this value equal to 1. The next setting is that the encoder is going to be connected to motor number 1. Now that we have saved this, we can switch over to the Analog Closed Loop tab. In here, we have the PID settings for the 6 motors, 1 PID line per motor, and plus we have a graph where you can display the current error or the current speed. Besides that, we also have the jog buttons, with which we can control the machine movement to immediately see what impact our movement will have on our error. So at this point, we can begin to set up our PID settings. And first of all, we have the DAC offset. This DAC offset is 12-bit, so it goes from 0 to 4095. And that, in real terms, corresponds to an output voltage of positive 10 volts to negative 10 volts. So within this range, we have to set it up so that a 0 from the PID controller will be equal to a 0 voltage output. Effectively, this DAC offset will correspond to either the motor not moving, or alternatively, if we can't get it to actually not move, it will correspond to a point where the motor is moving at its lowest speed possible. In my case, if I turn the motor on, so we send the servo on signal, then right now it will be producing about 2 to 3 rotations per minute. I'm just going to let it run for now. And if we go back into the encoder tab, we can see that as it rotates, the encoder values are changing. And we already have a value in the offset, in the DAC offset line, but if we change that offset to 0, then effectively we will not have any offset and the motor will begin rotating at essentially its maximum speed. And if we put in a value that's somewhere in the middle, between 0 and 4095, let's say 2080, then the motor will start rotating a little more slowly. And at this point we can begin to adjust this value, and we can play with this value to produce the minimum possible rotation, or if we are lucky, we can find a value that effectively stops the motor so it doesn't move at all. And now that we've found this proper DAC offset, something that produces either a minimal speed or a speed of 0, then this will be our DAC offset for the system. Next we have the K, which is the proportional speed coefficient. If the servo driver has velocity control turned on, its rotation speed will be proportional to the voltage output, and this coefficient will define the relationship between the two. Next we have the KO coefficient, which is just an additional coefficient, which is typically set to 0, and if we want to use it, it's just an addition to the exit voltage that will be functioning as an additional coefficient with the regular K. After that we have the Kp, Kd, and Ki coefficients, which are our proportional, derivative, and integral coefficients. And the next thing is our integral limit. And that is the limit for the integral portion. And this integral portion, without the limit, can otherwise be stored infinitely. And while that's going to be decent on adjusting small values or small error values, it will be a problem with large speed differences, simply because the values will trail behind a little bit. So here we can set a max value for the integral portion of our system. After that we can set an encoder channel. Here we have motor 1 and we have encoder 1, so that's what we're going to be set, but it can be assigned to any motor, any encoder. After that we have a dead zone, which is the error which is ignored. If you set everything properly, you don't really need it. We typically set it to 0, but it is something to consider. And the thing to do after that will be simply to turn on the PID regulator. So I have set the KP to be equal to 1. That's just the simplest scenario that we have. And what will happen is that the error, when it is at 0 or near 0, and the PID is on, then the motor will not go any further. And when you see these waves on the screen that are appearing right now, this is effectively me moving the rotor by hand, so I'm inducing an error into the system. So it moves a little bit, but it is resisting. It is trying to reduce that error. And if we set a higher coefficient, we can see that the PID controller is going to lower the error value. And if we increase the coefficient again, then the error becomes very close to 0, very near 0. So currently only the proportional coefficient is on, and this is all for the y-axis, what is assigned to as the y-axis. And if we move that, we can see that the error becomes very large. It's about 1500, or roughly 1/4 of the rotor rotation. So in order to see what else we can do, we can rotate this a little bit more to see how it impacts the graph. And we can also increase the speed from 600, which is about 10 rotations per second. And we want to increase it about 4-fold, so to around 40 rotations per second. At this point we can see that the error will grow, and our motor will be now moving faster. So here we can see that the system has automatically put in a value of 70 that has just now appeared. And what this is the system automatically calculating the speed of the motor and the corresponding values of the PID controller. And to rotate with this speed that we've given it, it will produce a certain voltage. The system will read this voltage and it will suggest to us a value for the base value of the K, which we've discussed earlier. And this makes our job easier. We don't have to set it up ourselves, and we have a rough ballpark estimate of what it should look like. So here, let's set, for example, 71, and we can see that the error will be nearly gone. And again, this error was at around 5,000, and now it's greatly reduced. So now, this is our very basic setup. You know, the error is probably around 50 to 100 markings on the encoder, and this is at 40 rotations per second. And after we've reached this point, we can effectively fine-tune these values until we've gotten them down to a level that we find acceptable. And after playing around for some time, these are the values that I found to work best with my machine, my setup, and if we save this, we can see how it looks like then. And again, my servo drivers they're more than 25 years old. They aren't very fine-tuned or anything like that. So you can see that the PID controller has to be set up on the real machine by the real user to effectively tune the values to the point where they need to be. And if we save this, the PID controller will be ready on the next run. And I will be linking a manual for closed loop setup, which should appear on the screen right now. And you can always find out more about closed loop setup on our documentation wiki. Thank you for watching.